variables. And a set of values that a continuous random variable can take is the set of all real numbers, denoted by the old-fashioned R. The probability distribution for a continuous random variable is specified by a function which is called the PDF, probability density function. The requirements must be met for a function to be a PDF. So that means not all functions are PDFs. Some are. They must have outputs that are positive only, so we can do that with an interval rule or a piecemeal. So think about interval, restrictions, and we could have piecemeal. I don't know if you did piecemeal functions, but they're there. And we want the total area, that is the integrated area, to be equal to 1. Does that mean we've got some maths coming up? Yes, it does. That means we're going to be a bit cheeky and look at some maths. So the probability that a random variable takes a value within a range is the area under the density curve. So probability and area under the curve are the same thing. Two forms expressed in a different way. So we can think of probability as an integral of f of x. So if we just think about this one here, probability is the area under the density curve. It has to be a PDF, and so we need means of computing the area. Now it's not always possible to do that, and I'll have some more to say about that next week. But for now, let's have a look at what that implications are. So for a continuous random variable, when we have x is 0, x is the probability of it being 0, then there's no area above the point, if you like. So to work out the area over an interval, what we do is we take the area domain, the interval domain, as our limits of integration, okay, and we place them in our integral. Now this particular form is a special type of integration which we don't cover in this course. So if you go on and do, I always ask students to do an elective in maths after they finish this subject, because I say, hey, come on, you love doing maths with me, you must want to do more. And so every year I get a few students, not a lot, but a few students who'll come back, and some of them will try linear regression, or they'll try linear algebra as a subject, and some of them will do advanced calculus or advanced maths and physics, which is basically the same subject. So in there we would call this an improper integral, because of this, the integrand intervals are plus and minus infinity. So you would learn how to deal with those. Even though I've got here, and I'm being a bit cheeky, we kind of defeat the requirements of plus or minus infinity by restricted domains. So that is, we put a restriction on the interval that goes into the integral, or we use a piecemeal function, and I'll show a couple of examples of that. So by the way, what math subject are you going to do for an elective? Are you going to do advanced maths and physics, or advanced calculus, or linear regression? I'm involved in that one too. And what's the other one I said? Linear algebra. How cool, you rule the world. So have a think about that. It can only add to your careers. Now I said that with a straight face, didn't I? I'm glad. When was the last time a maths teacher asked you to do more maths? Alright, so we'll talk a little bit about, that's a familiar thing there, so we won't dwell too much on that. Okay, so let's take a bit of an example. Now, in this particular question, it's talking about thin copper wire, the kind of copper wire you would get in a mouse cable, as opposed to the cable that feeds your iron or your heater. So it's a thin cable, and so it can't take much current. And what's current all about? Current is all about heating up things. Now, things are rated according to their heat capacity, and cables are no different. Combustion engines are. I told you that last time. But for this one here, we need to not exceed the current. Now we can turn this into a probability problem by measuring the current, and assume that x can take any value between 0 and 20 with equal probability. What is the probability that a current measurement is less than 10? So the function I'm going to give you, the function is an inverse proportional function. So for this point, it's 1 over 20. and we'll run with that as the given function that we're going to check the probability for. The probability step is that we're going to ask for less than 10. Okay, so if we set that up to do the integral, we've got a restricted domain. So we're looking for 0 to 10. We're going to integrate 1 over 20 dx. Some of you might rush and say, let's pull that out and do 0 to 10 for dx. Some of you may have seen it that way, and that's okay too, in which case in your mind's eye that would be a 1, and you'd just be integrating 1. Either way is fine. For some of you, you'll be thinking integration and you'll be starting to cry. Don't cry, it's all right. I want to show you the only thing you need to know for integration in this course. And that, I don't know if Ara would be happy with me saying that, but certainly in the stats part. Okay? No, not here. I'm not going to explain why. This is an inverse proportionality, and that's the most I'm going to say about that at this point. So yeah, current is inversely proportional to the resistance of the wire, and so at this point that's as far as I want to take that. What I do want to do is say what I said about the integrations. So if I'm integrating 6, what do I get? If I integrate 6, what do I get? So this is a bit of revision, but I find it helpful. What would I get? If I integrate 6, what will I get? And it goes to this notion, yeah, 6x plus c. So it goes to this notion that I'm actually integrating 6 times 1, and I'm actually integrating 6x to the power 0, and when I do up and under on my rule, I'll get 6x over 1 plus c, which is 6x plus c. So for some reason that's a stumbling block for students, so I'm just kind of eliminating it. So either way, whether you leave the 1 on 20 there or just integrate that, where before you had no x, there will now be an x. Okay, so where before you had no x, there will now be an x. So where before you had no x, so I like to do this because this is more like what you'll be doing in your maths part a bit later on. Okay, so when you're integrating nothing, you're not integrating nothing, you're integrating 1. Or you're integrating dx, that's very confusing. 1 in disguise. Okay, so if we go ahead and do that, I'm going to integrate this one. You can lay it out however you like. So I'll have the x will appear between 0 and 10 by the fundamental theorem of calculus, which is going to be equal to 10 over 20, subtract 0 over 20, and so that will go out, and then we will have 10 over 20. So there's a 50% chance that less than 10 milliamps will flow in this particular circuit. A 50% chance. So who knew of looking at the probability of current flow in a circuit this way? So I haven't dropped any hints yet, so don't be alarmed, we're just walking through this. Let's think about the qualifications to be a density function, and that was here, so it had to meet these criteria here. How do we put that into practice? So here's a piecemeal, piecewise function. It has 2 parts to it. One of the parts is the function value over a restricted domain, and 0 otherwise. Okay, so let's see if we can ascertain the 2 conditions. We want the sum to be 1, and we also want the function should always be positive. So we can do both of those. Yes, I know, doing things by hand, is it always positive? So let's check that. Okay, so just remember, anything that's got greater than 0 in mathematics is such and such is positive. Okay, so we put our function together. 1 minus y squared is greater than 0. Now if I multiply by 2 and divide by 3, they're constants, so it won't affect the sign. So I'll end up with 1 minus y squared. Likewise, if I add the y squared over the other side, it's a positive, so I've got y squared. So that will end up being y equals plus or minus the square root of 1 plus or minus 1. We express that in an interval. I don't know how much of that you've done, between 1 and minus 1. And because of the constraint, if we get to 0, otherwise. So if we try and go to here in the domain, we'll get to 0. And we've got that up here. So f of x is positive. For the restriction in the domain. So we have a tick. Very good, we did that. For our rather convoluted integration, we want to see if we can go improperly. Well, hang on, Jason, we haven't done improper integration. You can't put that up. You haven't told us how that works. I know, but I've got a restricted domain. And because I've got a restricted domain, it's not such a big deal. So that looks very much like your ordinary run-of-the-mill integration. So whether you take the 3 on 2 out or whether you don't, it's entirely up to you. Some of you will be annoyed by what I just did because you'll be so used to taking it out for later calculation. But that's okay, that's what the fun of life is, isn't it? We all do things differently. And as long as we get the correct end. So we've got our fractional parts, and we've got 3 on 2 minus a half, and 0 on 2 minus 0 on 2, so that's gone. And so 3 on 2, 1.5, whoops, 3 minus 1 on 2 is 2 on 2, and so the integration over that interval is in fact 1, so tick, it is a PDF. So it is a valid probability density function. So I'm not warning you, I'm not trying to frighten you, I'm just showing you some of the maths that's in statistics. You can take statistics anywhere you want. You can have as much or as little maths as you want in the statistics, depending on your approach and how the areas that you want to look into. But the explanations are there in the maths of the statistics, if that makes any sense. So this is meant to be part of the educational awakening, if you like. Okay. So I'll let you do those as an exercise, just for a bit of fun. Okay, and I'll let you do that. Alright, we're going to have a look at the cumulative distribution now. So the cumulative distribution function, f of x, and what's the main difference? There it is. It's not equal, it's less than. So all of these values that are being read off the table have come from some form of computation like this. Now the computation is not straightforward, and I already said I'll have more to say about that next week, but it is rather convoluted, and I'll explain some of that next week. But for our purposes, we know that we can't do an improper integral in this way, so again we're going to have domain restrictions and the like to answer that problem. The cumulative density function of a continuous function can be used to determine probabilities, so that's helpful. Probabilities can then go on and compute means and statistics for us. Using this idea of the fundamental theorem of calculus, and then we've got a familiar area under the curve, which is a composite of a subtraction. So it's not terribly difficult. I'll give you a hint of the type of integration that I want you to be able to demonstrate as we go forward. Alright, so let's have a think about our little example before. Oh, well, do we have to do the integration? Do I have to do all that? I thought we did that before. And the answer is no, I don't. Okay, we can take the function value at x equals 10. And that is, oh, actually I want to put that in as a function value, not a variable, sorry. So put that in as put 10 in, and what do we get out? We go and find it, and we'll get 0.5. So where it's printed for you, that's as much about using the properties of the distribution functions as we want you to have at this point, because again, as I said, you have to go and do the subject probability or advanced statistics to do some more on this. But these values are the result of integrations. So isn't it good when we give you a table? Whoa, go to the table. Alright, so having said that, we can develop equations for our means. Again, obviously, with an improper interval, how do we address that? We constrain the interval, the domain interval. Okay, and we may even select certain functions that have properties that lend themselves to this, and I'll explain that in the next section. So we have x times f of x and x squared times f of x. Oh really, does this mean Jason's going to do a whole lot of hand calculations? Yeah, I love it, isn't it great? Okay, so we're going to do some hand calculations, that's fun. Why not? Okay, so the amount of time, now I'm going to use that value as less than 10. It probably should be 9, shouldn't it? Yes, you're probably right, but I'll have a look into that. I'll give you a more precise. That example is just an introductory example, so I'll give you a better answer. Let me work on that and I'll get back to you, okay? Alright, for this one, find the mean and standard deviation for the amount of time that the train is late. Okay, if you like. So we've got functions of y, so our expected value for y is this rather complicated looking y times f of y and dy. So we've got our function which has now got the constraints on it. Oh well, that makes it a bit easier. Minus 5 to 5 y times 25 minus y squared, and we're going to compute a mean value. Remember, this is a mean. Okay, so you can do the expansion, that's probably the easiest thing to do. So we put the 3 on 500 out, minus 5 to 5, 25y, whoops, (25y minus y cubed). That's just the result of the expansion. And so we'll get 3 on 500 outside of, now we can do the integral. Okay, so that's by FTC, and so we'll end up with, now if you go ahead and do that, and I'll leave you to verify that, we'll end up with 0. Okay, so in this particular distribution, we shouldn't be surprised for unexpected results. It is symmetric, plus or minus 5. If you think about the nature of that quadratic, that's not a surprising result. Okay, but anyway, we won't spend too much time there worrying about that. Okay, what we want to do is use that result to get our terms that give us our deviations. So we've got our y term. Now if we go ahead and repeat all of that for y squared times f of y dy, okay, and I'll leave that for you to do as an exercise, you should come up with a result of y 5. If we put the variance for y together now using our two results, that's that one, and that was mean was 0, wasn't it? So that one's 0 squared. So we have 5 minus 0 equals 5. And so our standard deviation for y is the variance for y, which is 2.24. So you're learning where the computer is getting its values from. Okay, why we yes, you should get a formula sheet. Ara will confirm all of that stuff. Okay, Ara will confirm all of that stuff. So it's not terribly difficult, but we're just taking you through how the computer gets to it, because you guys are very smart and you're well qualified to understand how a computer system pulls in this information. I'm going to leave this one as an example for you to have a go at. I'll populate the results. So the mean should be 3 on 8, which is about 0.375. So I'll let you work this one out. The term that's needed to work out the variance is 0.2. The variance itself is 0.59. Now this is where you have the discipline to sit down and do these, okay? It's the square root of 0.059, and you know, I'm an old dude, so back in the day, guess what, there weren't any computers. So everything had to be done by hand. Alright, so that gets us through random variables and some computations for probabilities to get our means and standard deviation, etc., our variance. So we're going to have a look at the last one, which is exponential distributions. So now's a hint. Okay, so I'm going to give you a hint. Alright, so what do we know about exponential functions? Well, first of all, if I do this function, it's y equals e to the x. Okay, so if I go off to infinity, the value for y goes off to infinity. That's fairly self-explanatory. Okay, y would go to infinity. But what about if I have y equals e to the minus x? What's that one do? Okay, so this is the one that comes down. So that's 1. So we'll do 1 there. This is the one that comes down. Now what's happening to this function as x approaches infinity? What's y doing? Y is approaching what? What does y get? Y gets 0. Okay, so this reduces, yeah. So this is another way of us getting around having these rather difficult integrations, improper integrals. Okay, so we use these functions. Now, this particular function, if a random variable x equals the distance between successive events, then in a Poisson process, then lambda is positive. Sorry, let me read that again. If the random variable x equals the distance between successive events in a p process with a positive mean of lambda, then it has an exponential. So the exponential, this distance between successive events, is hiding the fact that it's the time. Okay, it's the time between events. So the exponential and the Poisson are good together because one tells you the count of events and the other one tells you the time between events. So it's often used in processes are that model lifetime, start time to finish time, or time between events, or the inter-arrival time, traffic again. So there you go. So we can calculate using this particular example for an exact value. So that would be the case where we would have px equals. We could plug that straight in. Otherwise we'd have to use the PDF, and you guessed it, the PDF is going to be an integral. So in this case we've got our mean, which is simply 1 over lambda, so that's slightly different to the Poisson, so just watch out for that. In the P distribution it was just lambda, here it's the inverse, and the variance is the inverse squared. So we just need to be careful of that when we come to do calculations, and I think it's a time to do some calculations. Alright, so I'm going to put, actually I didn't put it on that last slide, did I? I'm going to put a great big asterisk here. That's a hint for the final exam. Okay, so this is a hint for the final exam. Now, the time between arrivals of emails at your computer is exponentially distributed with a mean of 2 hours. Well, thank you very much. What is the probability that we do not receive a message during that 2-hour period? Okay. So the first thing we've got to do is identify the mean of 2 hours. So for our exponential distribution, our expected value is 2. However, looking carefully, our expected value is the inverse of lambda, or lambda is the inverse of the expected value. So please be careful with this. Okay, so we've got, it doesn't matter whether it's a decimal or not. So we've got our lambda, and we've also got our computation. Now if it's going to be exact, we can just plug it in. If it's not, we have to integrate it, and that is something I do want you to be able to demonstrate. So the most difficulty you'll have is U substitution integrations. I don't think it's unfair to point that out. So the probability of the inter-arrival time being greater than 2. So there's our greater than 2, and we can compute this. So we'll have our integral from 2 to infinity, lambda e to the minus lambda x. Remember that lambda is a fraction, so it's going to look weird. And we're also using the property of a negative e to the x, which goes down to 0 as x goes to infinity. As x goes to infinity, okay, this term here, this whole term, goes to 0. Okay, alright. So that's the other way we're getting around this, because we haven't constrained this at all, it's just infinity. Oh, okay. So the next thing we want to do is, now these will work just like any U substitution. So you can go through and do that for yourself. So we've got a substitute, our lambda is a half, e to the minus, because that's the equation, a half x, or x on 2, it's up to you how you do that, dx. Okay, so we can go through and do the usual thing, Leibniz notation, swapping everything around. So if we substitute out that, we'll replace it with this. Now what you'll notice is the 2 will cancel this half, so that'll disappear, and we'll have a minus out the front of the e. Yes, you can go ahead and do the reallocation of the limits because of the change of variable. You can do it, it will still work. However you decide to do that, I'll leave that to your imagination. But for my part, I'm just going to take the shortcut, which I know is very rude of me, by FCT and so that becomes minus e to the minus infinity on 2 minus e to the minus 2 on 2. Okay, so what's going to happen to this term? What's happening to this term? I've said it 3 or 4 times already. It's going to become 0. So we'll end up with 0 minus e to the minus 1, which is simply 1 over e. Yeah, that's right. Oh, you guys are smart. I know you're all very good. 3, 6, 7, 9. So we've got a 36% probability, 36% chance that we don't get a message during a 2-hour period. So that's how we decompose that problem. But again, I just want you to be able to do one of those after the student vacation. You'll get a chance to see some past papers, I think. I'll talk to Ara about that, and this will be an expectation, I think. Okay, so it's about 3 seconds. Okay, if you're asking that question, it's about 3 seconds. So I've been pretty good at managing you not seeing that, I hope, but a couple of you have noticed it, obviously. It's purely just the transmission time. It's like delay. Okay, so again, if we take a look at the mini printout, we've got this going the wrong way for our purposes. So how do we overcome that with a PDF that's going that way? Okay, how do we overcome that? It comes back to that same question. How do we turn the sign around? So I can show you, I've got a little screen that shows me the real-time output there, and so when I'm turning my head or when I'm doing that, I'm actually marking myself and watching when it turns up, so that's a bit cheeky. But for example, I could do this. 1, 2, 3, 4, 5. There it is, it popped up. So that's just to show you how it works. Alright, so for this point here, we've got 1 minus, we turn the inequality around. Okay, and we've got 1 minus this one, 0.6, 1, 2, 1, and so we get 0.367,878, which is close enough to 0.3679, and guess what? There it is, up there. They're the same. So either way, you're doing integrations, but I'll say more about that next week. When you look these tables up, you're doing integrations. I'm just giving you the exposure to how you do that. Okay. All right. A little more info about this. We're getting pretty close, so that's good. And just a little bit of revision. Poisson and exponential distributions are related. So we say x such that it's a Poisson distribution. That's how we would write that, is the number of times, so that's the count, that an event occurs in a fixed interval. Then y such that it's an exponential distribution is the interval between the 2 consecutive events. So they are used together. That is, the frequency of an event takes the p distribution and the period of the event takes the exponential distribution. Okay, so what is the probability that we receive 3 emails in an hour? So we'd use the exact one. Okay, in which case we can just substitute the equation generally. And we can get 0.0126 as a probability. So it's a very different way of looking at statistics, isn't it? It's a very different way. Alright, so there's another concept now that comes up. The concept that we'll come up with is the notion of repeatability, independence, expressed through the lens of an exponential distribution using probability. So in an exponential distribution, the probability that an event will occur for a certain period of time in the future, what's that interval going to be, does not depend on past behaviour. So again, as a concept, not so much the computation, but certainly as a concept, that is something that we'll be interested in having explained. Okay, so what is it? It just means that there's independence between periods, so that when you go from one period to the next, what happens in the next period didn't get affected by what happens in the last period. Okay, now the way that we express that is that given period A, this is a phrase called given that, this vertical line. Okay, so given that x was greater than A, x will be greater than B. So we can compute that. It's a fairly simple computation. I think I've got an example, but I'm not highlighting so much the computation as I am the concept, okay, because of independence. So very quickly, if you haven't received a message in the last 4 hours, what will the probability be that you did not receive the message in the 2 hours? So that'll be 6 and 4. So it'll be x is greater than 6 and such that x was 4. So the probability will be, you had to compute that 6, but did you notice that? X is 6 minus 4, and so that's the probability of x greater than 2. And 0.3679, and then if the probability, if you've not received a message in the last 6 hours, what is the probability that you did not receive a message in the next 2 hours? So again, you've got to work that through. Okay, so we've got the probability of 6 and 2 now, not 4 and 2. So that means we're going to have a variable 8, given that our delay is 6. So our difference will be 2, so it'll be 8. X is greater than 8 minus 6. So we'll get x is greater than 2 again. So we get that same 0.3679. Alright. And finally, I think I've got, what is the probability? An exponential distribution. So this is helpful. So I certainly would want you to be able to process this with a mean of 150 hours. So expectation is 150 hours. So that means our lambda is 1 over 150. What is the probability that the machine is not broken down after 50 hours? So we want the probability of success to be greater than 50. The probability for success can be created from 1 over 150 e to the minus x over 150 dx, and we get 1 over 150. Again, going through all of your u substitutions here, setting this up so that you get the e will cancel out the 150. Okay, and we've got 50 and infinity. And the basic expectation is that you would be able to do that, minus 1/3, and so we would get 71.65. Alright, so that's calculating that. So part B, there's another part. Suppose the machine has an operational For 60 hours, what's the probability that a single machine will still be operational after 110? So it's an exponential distribution. Why can we say this? We can say this because of the memoryless property. Okay, it'll be the same probability possibly. So we could go ahead and compute that, and would we get the same one? Let's try it quickly. So we would have to have x is greater than 110. Given that x was 60, if x was 60, we'd get x is greater than 110 minus 60. So that gives us the probability of x being greater than 50, and that's the same as before. Why do we say that? Well, simply because of this is due to the memoryless property. One interval doesn't affect the next. Okay, and I'll leave it there. All right, so okay, so we have the question asking us is not broken down after 50 hours. So we want to check post 50 hours. Post 50 hours to infinity. So we just assume that the first interval, it's independent. This is this memoryless property. So the first interval is not going to be part of it. So we're looking just purely from 50 up to infinity. What's the probability of it going 50? And that's the same language that in saying that the machine's not broken down after 50 hours. Because it doesn't specify how much after 50. 51? 50,000? It doesn't specify. So we just integrate over that longer period of time, and the probability will give us an accurate picture regardless of what that next breakdown is. But the exponential distribution is independent in that regard. Alright, so hopefully that's answered that for you. What I'm going to do is pause there, okay? And we've gotten to the end, so thank you very much for coming along. I'll have some information about know-how sessions very definitely for next week, because we really need to get those underway. And that'll be just, that's more likely to be on Zoom. But I have run those, in the past I've run those two ways depending on the number of students. I have done a live stream and Zoom at the same time, so that you can hop off and just look at what's happening and then jump on and ask a question. So we'll just see how it goes. Just play it by ear, but I've got the capacity with technology to make sure that it's a good fit no matter how many turn up. Alright, what I'm going to do is press pause there and say thank you very much for coming, and have a good weekend, and I'll see you next week. Good job.